Hi everybody, this is the notes for 6.5. This is Ms. Dinkelman. We're going to do this in two parts. So this is part one where we're going to talk about the second fundamental theorem of calculus, and then I'll stop and then I'll do a part two for the integration involving natural log. So Gary's kind of setting us up here to kind of understand what's happening with the second fundamental theorem. So if we were to take the antiderivative here of number one, we're going to get f of t. And then again, remember, as we're calculating integrals, we kind of write that vertical bar, and then we plug in the upper limit and subtract and plug the lower limit in. So now on 2, what this is asking us to do is take one more step. So now it wants us to take the derivative, and I'm going to think, okay, I'm going to take the derivative of that thing I just got. And the derivative of that would be, okay, well, f prime of x minus, now f of 10, think about what happens if we take 10 and we plug it into a function. We get another number spit out. So something happens with the 10 and there's a function that tells us what happens with that, but we get a constant. And when we take the derivative of that, we're going to get 0. So that kind of brings us to what happens with the fundamental theorem of calculus here. And that is, if I try to take the derivative of the integral, I basically end up with the original function, but what I want you to notice for the answer is that the x now goes there instead of having a t. Okay, same thing happened up here on number 1. When we took the antiderivative and plugged in the x, again, we changed from an x to a t, but then we went back and we got this exact f prime of t, but instead there was an x in it. So that means when we do these, we can kind of take a shortcut as we're doing them. Now I wish we'd do a couple of examples really quick. I want to see if there's one in here where it's just an x. I know I'm going to skip ahead a little bit. Perhaps. I'm going to do number 7. So first of all, for number 7, I'm going to rewrite it. I would really like the x to be on the top, and we may or may not have talked about what happens if we decide to flip those signs, and that is just that we end up getting a negative of what we had before because we're just taking area in the opposite direction. So what I'm telling you is when we take the derivative of this integral, maybe I should pop that negative on the outside there, we're going to get this original function, but instead of a t, we're going to get an x. So it's going to be 2x minus 3, but again, because I had to flip those, that's going to be a negative right there. Okay, let me just make up one more. So if I asked you to take the derivative of the integral from, let's say, 7 to x, and let's say it's a little bit of a crazier function, so sine of t squared dt, something we actually don't know how to find the antiderivative of. What I'm telling you the answer is just this original function with an x plugged in, because the derivative and the integral are basically inverse operations and should cancel each other out. We should just get the original function. Okay, so they're going to step us through, okay, what if it's not just an x? What if it's an x squared? So let's talk about what happens there. So again, we're going to take this integral, so we would get the antiderivative, so just f of t, kind of do our new notation with the vertical bar, and we'd plug in the x squared, and then we'd plug in the 0. So now on 4, they just want us to take the derivative of that thing. So the derivative of f of x squared, well, suddenly this is chain rule. So the derivative of the outside would be f prime of x squared, leaving the inside alone, right? And then times the derivative of the inside. And then for f of 0, derivative of that, still 0 again. So let's look at the trick we could do here. We can still do this thing where we take the x squared and we stick it into that original thing in the integral. It's just that we have to now include the derivative of that x squared, which is 2x. Okay, so let's maybe just do a quick example similar to that. So let's see, if I give you the derivative of, let's say, 3 to 5x, and let's go square root of t squared plus 2. All right, so the trick is I can just take this 5x and plug it there for t. So my answer should be the square root of 5x quantity squared plus 2. But then what I just mentioned was we also have this extra where we have to take the derivative of that thing. So there's a 5 there that I need to put down there because the derivative of 5x is 5. Okay, and then we hardly ever see ones that have variables in both locations. Normally it's a variable and then just an x value in one of them, but let's go ahead and talk about just in case. So we would take the antiderivative, which would be f of t, and then we would plug in. And then on 6, again, same question, they're just asking us to take an extra step. So what's the derivative? So for f of 2x, it's going to be the derivative of the outside, leaving the inside alone. So it's still 2x on the inside, and then times the derivative of the 2x, which is a 2. And then the f of x cubed, so derivative of the outside, leaving the inside. So really the same trick. We just get to plug in, okay, that upper limit into the original function and then multiply by the derivative of that. And then the same thing happens with the lower one in this case, since it's a variable, plug it in and make sure you multiply by the derivative of it. Okay, so that's just because of chain rule. So Gary kind of tries to explain that here with the v primes and the u primes. So we have to make sure that we put the derivative of that thing there as well. Okay, so let's go to some examples and see if we can employ the trick without having to actually take the derivative. So one thing you can do that works is you can just always plug the things in now that we know about this chain rule issue. Plug the 5 in, so 10 minus 3 is 7, and what's the derivative of 5? Well, the derivative of 5 is 0. And then we would plug the 2 in, so 4 minus 3 is 1, and then the derivative of 2 is 0. So the answer to this one is just 0. And you might have known that to begin with just because of the plugging in part. So my preference on these, so number 9, again, plug the x cubed into there. So it's going to be x cubed squared plus 2x cubed. Okay, all of that times the derivative of x cubed. And I actually stop at this point knowing what's going to happen. But if you want to do it just to help yourself remember, the next thing I would do is I'd plug in the negative 1. So that'd be a 1 minus 2, and then the derivative of negative 1 is 0. So that's why that's 0. Again, I tend to not put it because I know what's going to happen. Number 10 is asked in just a little bit different way. It gives us f as the function, but the function has an integral, and then it wants us to take the derivative of that. So we have to take the derivative of the integral. So again, the trick is I'm just going to take that 3x squared and substitute it in for the t value at 3x squared. Again, I'm not going to do the other part because I know what's going to happen, and that is it's going to be multiplied by a 0. Okay, so on the assignment, that first few, 1 through 7, are basically just like that. I think they sneak one of there. Number 7 looks like it's not a derivative. So that's where you're practicing that particular idea. You have, you should be, oh, actually 1 through 8, sorry. You can do 8 too because I see that integral in there. There are some integrals in here that you're going to know and some that you don't because it's going to be in the part 2 part of the notes, but you're welcome to get going on those. And then just as always, there's the review problems at the end. So you should be able to bang out some of those. But go ahead and at least get to 1 through 8 there because that's the idea we just talked about. And then you can watch the part 2 video and finish up the assignment.